Okay, so in this lecture we will briefly discuss the concept of exponential matrices. Exponential matrices. Okay. The sole goal of this lecture is to just give a structure of what exponential matrices are and a problem to explain how it works. There are several analytical discussions on exponential matrices as well, but I won't be discussing those in this lecture because that discussion is quite rigorous and I don't want to keep this in this discussion at least. Okay, so now what is the expansion of e to the power x? If you recall, so the series expansion of e to the power x is, so we know that this expansion is somewhat of this form, right? So it's summation n equal to 0 to infinity x to the power n by n factorial, right? Or you can write it like say 1 plus 1 upon 1 factorial plus, so then it becomes, sorry, x upon 1 factorial, or let me write it as x simply, x plus x square by 2 factorial plus x cube by 3 factorial and so on, right? Okay. So if A is a n cross n real or complex matrix, let A let A be a n cross n real matrix or n cross n complex matrix, then we define the exponential of a matrix as the same series where we just replace the identifier x by the matrix A. Okay, so it's a to the power n upon n factorial, and that's the exact definition. Okay, so similarly, if you have some scalar t for some scalar t e to the power ta will be defined simply as summation n equals to 0 to infinity ta to the power n upon n factorial, right? Obviously, you can bring t out, but that's quite trivial. So immediate observation is a set of theorems. These theorems will obviously need an analytical proof, but we are going to assume that they hold, and obviously we consider them as theorems. So theorem number one, suppose I name this series to be 1. So theorem number 1 is that the series 1 converges absolutely, converges absolutely and uniformly on bounded sets of complex matrices, on bounded set of complex matrices. Number 2 is that this exponential matrix e to the power ta, where t is obviously a scalar, this is a differentiable function of t, is a differentiable function of t, and its derivative is the matrix product. Its derivative is the matrix product a times e to the power ta. Now it's quite obvious that this series is a series of matrices, right? So it's sort of a matrix. Okay, infinite sum of matrices, and A is itself a matrix, so it's a well-defined matrix product, right? Dimensions hold for matrix multiplication. because the e to the power ta will each matrix in the summation will be of dimension of a, and so the matrix multiplication is quite obvious. And the third theorem says that let a and b be complex matrices such that they commute, such that they commute. Then the exponential law holds. That is, then e to the power a plus b equals e to the power a times e to the power. Okay. So these are the three important, you might think of it, you think of them as properties of exponential matrices. The proof of these theorems sort of requires the concept of norm of a matrix. Okay. We define the norm of a matrix as the maximum of the entries of A. The maximum of the entries of A. So let's say I. So we are considering an n cross n matrix, right? So this is the range. Okay. So this is sort of the definition of a norm of a matrix. And there are two important theorems due routine which will help us solve these theorems, but we are not gonna discuss them in this lecture at least. Okay. What is an immediate corollary of this theorem? Corollary. The first corollary is that for all matrices, complex matrices, e to the power a is invertible. E to the power a is invertible, and its inverse is e to the power minus s. Now it's quite obvious, right? Because if you consider the third statement, then a and minus a commute, right? It's minus a times a. Therefore, we can consider e to the power a plus minus a to be e to the power a dot e to the power minus a. Therefore, e to the power a plus minus a is same as e to the power a dot e to the power minus a, which is, so this becomes e to the power 0. E to the power the 0 matrix, right? So this is e to the power the 0 matrix, which is equal to e to the power a dot e to the power minus a. Now, if you carefully calculate the e to the power 0 matrix, what will it come out to be? It will simply come out to be e to the power 0. Okay, 0 being the real 0. So then it becomes 1, right? Is it? I guess it's clear. You can obviously calculate this directly from definition. What is e to the power 0? So it's summation n equals to 0 to infinity 0 to the power n upon n factorial. If you let us just observe it from the point of view of a 2 cross 2 matrix, let's say. Okay. Let 0 be this matrix 0 0 0 0. Therefore, what is e to the power o? Let me just tell it to be o. So it's 1 plus, then you have here 0 0 0 0 upon n factorial, plus you have here 0 0 0 0 squared upon, sorry, it's 1 factorial, here you have 2 factorial, then have 0 0 0 0 whole cube upon 3 factorial, and so on, right? So you get the identity matrix, right? This one is basically I. Right? Are you getting my point? This is a 0 matrix. This is also a 0 matrix. This is also a 0 matrix. So all these parts are 0 matrices, and this comes out to be the identity matrix. So e to the power 0 is the identity matrix. So this implies e to the power a dot e to the power minus a is equal to the identity matrix. Now I use the term that 0 n, I mean the n cross n 0 matrix eventually seems like e to the power 0. So I actually meant that e to the power 0 in the sense real 0, I use the term real 0. So I actually wanted to use the sense that initially we had said that a to the power 0 is identity. I have not written that right. Yeah, so we obviously consider this assumption in 1 that a to the power 0 is identity. So I wanted to say this typically. Okay. Clear? Okay. Yeah. Now calculating e to the power a when a certain matrix A is given, it's quite tedious, but it's also quite easy if A is a diagonal matrix. Okay, because consider a diagonal matrix D which is of this form. Say it's lambda 1, lambda 2, lambda n. Then obviously what is d to the power n, m, let's say. So it's just the diagonals raised to the power m, right? So until lambda n to the power, right? M is a natural. Clear? Also observe the fact that if A is a diagonal matrix, if A is a diagonal matrix, then suppose A is of this form. So it's lambda 1, lambda 2, so on till lambda n, right? Then e to the power A is this diagonal matrix. It's e to the power lambda 1, e to the power lambda 2, and so on till e to the power lambda n. Okay, let's just verify this. It's very easy to verify. So we suppose this is A. Okay, then what is e to the power A? So by definition, it's summation n equals to 0 to infinity a to the power n by n factorial. So this is summation n equals to 0 to infinity. So by definition, it becomes lambda 1 to the power n, lambda 2 to the power n, so on. Sorry, yeah. So I have lambda n here, right? Let me just change the index of the diagonal values. So let this be m. We don't want to mismatch the index. Okay. So you have lambda 2 to the power n, and here you have lambda m to the power n upon n factorial. So n factorials are typically constants, right? So you can just put them inside under a summation form. Summation goes inside the matrices, right? So this is this matrix form, right? So it's summation n equal to 0 to infinity lambda 1 to the power n by n factorial. Then we have summation n equals to 0 to infinity lambda 2 to the power n upon n factorial, and so on and so forth till you get summation n equal to 0 to infinity lambda n to the m to the power n upon n factorial. But these elements by definition, so the diagonal entry, so this is the diagonal entry consists of lambda I summation lambda I to the power n of, wait a second. So the diagonal entry consists of summation n equals to 0 to infinity lambda I to the power n upon n factorial, I ranging from 1 to m, right? Now what is this? This is by definition e to the power lambda I, right? This is by definition e to the power lambda I. Then so each entry, so this becomes e to the power lambda 1, the next entry becomes e to the power lambda 2, and so on and so forth. It becomes e to the power lambda n. Got it? And this is very important also. Okay. Clear? Let us consider a few examples now. Let us first consider a very trivial example. Example 1, let's say. So suppose the matrix A is given as 1, 2, 1, 0. Okay. Let us first, calculate it trivially, what it comes out to. It's obviously a diagonalizable matrix because the eigenvalues of A are 1 and 2. So you have distinct eigenvalues, hence it's diagonalizable. But we're not going to calculate the diagonal matrix right now. We first want to just simply evaluate it. Okay. Now the evaluation of e to the power A obviously depends on the fact of the powers of A, right? So let us first calculate inductively what is the power of A coming out to be. So what is A squared? So it's 1102 times 1102. So this comes out to be, so 1 times 1, you have 1 here, You have 1 times 1 and 2 times 1. So you have 3 here, you have 0, and you have your 4, right? So then what is a cubed? So a cubed is a squared times a, right? So 1, 1, 0, 2. So this comes out to be, you have 1, then you have 1 times 1, 3 2 is 6, 1, 7. Here you have 0, and here you have 8, right? Then what is a to the power 4? So this will help us to construct the form. So it's okay. Let me just, so it's a squared whole squared, right? We calculate it via this. So it's a squared 1304, 1304. So it's 1 here, it's 16 here. It's not quite getting quite obvious. And here you have 1 times 1, 1 times 3 plus 12. So it's 15, right? And here 0. So obviously the element in the second element in the first row, it's just 1 less than the second element in the second row, right? And it will trivially continue. I guess you have already guessed the pattern here. So therefore a to the power n, if you carefully observe, so the first element always remains 1. The second element of the second row, it's actually 2 to the power n if you observe. So you had 2 in the a to the power 1 had 2 here, a to the power 2 had 4 here, a to the power 3 had 8 here, a to the power 4 has 16 here. And this is, we just noticed, it's 2 to the power n minus 1, and you have 0 here, right? Is clear? You can also calculate a to the power 5 to verify it. You can obviously proceed by induction. You have written a to the power n in this form. You can just calculate a to the power n plus 1. Let me just be pretty sure of the fact. Then what is a to the power n plus 1? So a to the power n plus 1 is carefully a to the power n into a. So it's 1, 2 to the power n minus 1, 0, 2 to the power n times. So what was a? So it's 1, 1, 1, 1, 1, 0, 2. Let's just calculate it out. So it's 1 here. So it's 1 times 1 and 2 to the power n minus 2 to the power n minus 1 times 2. So it's 2 to the power n plus 1 minus 2 plus 1, right? 0. And here we have 2 to the power n plus 1. So it's coming out to be 1. This is 2 to the power n plus 1 minus 1, 0, 2 to the power n plus 1. Okay. Right. Therefore, we have got this pattern by induction. Now, if you want to calculate e to the power a, so e to the power a is summation n equals to 0 to infinity a to the power n upon n factorial. Now, you simply put the value of a to the power n, which you have got. So it is 1, 2 to the power n minus 1, 2 to the power n here, 0 here, all upon n factorial. Then it becomes a matrix summation. So it's summation n equals to 0 to infinity. This is 1 upon n factorial, right? This is summation n equal to 0 to infinity. This is 2 to the power n minus 1 upon n factorial. This is summation n equal to 0 to infinity, 2 to the power n upon n factorial, and you have 0, right? So what does it come out to be? So this is by definition e to the power 1. Now you can separate this out as summation n equal to 0 to infinity 2 to the power n by n factorial, which gives you e squared, minus summation n equal to 0 to infinity 1 upon n factorial, which is 1. So it's e square minus e. And here you have e squared, here you have 0. Right? Is it clear? Now what if we diagonalize it and then find out what will happen? So let's just consider the diagonal form of it. Okay. Now a is given of the form 1, 1, 2, 0. Right? Right? Okay. Then what is the characteristic polynomial of it? Now it's quite obvious though. So I'm not calculating it anymore. So the eigenvalues of A are 1 and 2. Right? Therefore, clearly A is similar to a diagonal matrix which is of the form 1, 2, 0, 0. But we need to write A equal to something. Otherwise, we won't be able to calculate e to the power A. Right? But we know that in this case, there exists invertible matrices. invertible matrices P, invertible matrix I should say, invertible matrix P. Uh, so it's let's say GLNC, such that A is PDP inverse, right? Clear? So this implies, okay, so we have this form. Now what is e to the power A in this case? So let me just come out with a general form. Suppose A and B are n cross n complex matrices, and P be a invertible complex matrix n cross n, such that A can be written as PBP inverse. Then what is e to the power? So e to the power A is nothing but, by definition, it's summation n equals to 0 to infinity a to the power n by n factorial. But if we can replace a to the power n by p inverse whole to the power n, right? So it's summation n equal to 0 to infinity. So it becomes p inverse whole to the power n by n factorial. But it's obvious to observe that p inverse whole to the power n is nothing but p to the power n p inverse, right? So it's n equal to 0 to infinity p to the power n p inverse upon n factorial, right? But then by associativity, sorry, by distributivity, p and p inverse can be taken outside. So it's p summation n equal to 0 to infinity b to the power n by n factorial into p inverse, but this is nothing but p e to the power b inverse, right? Therefore, if A is diagonalizable, then we have this form. So therefore, if A is diagonalizable, to a diagonal matrix D, then there exists invertible matrix E, such that A can be written as P D P inverse. But then that implies e to the power A, by what we just observed, is P e to the power D P inverse. And we know how to calculate e to the power D when D is a diagonal matrix. So if D contains in its diagonal lambda 1, lambda 2 to lambda n, then e to the power D will just contain the diagonal e to the power lambda 1, e to the power lambda 2, and so on until e to the power lambda n, right? So we just need to calculate P and P inverse, that's it, right? Okay. Like if you recall how a to the power P D P inverse comes out in when A is a diagonal matrix, this P consists of eigenvectors, if you recall, okay, along the columns. So what is AP? So AP is of the form, suppose say it's V1, V2 till Vn, where each of V1, V2 till Vn are eigenvectors associated with eigenvalues lambda 1 till lambda n. Okay, then it's of this form. So it's AV1, AV2 till AVn. But by definition of eigenvectors, so this is nothing but lambda 1 V1, lambda 2 V2, so until lambda n Vn. But then that is exactly equal to the matrix V1, V2 till Vn times lambda 1, lambda 2 till lambda, right? So these are the columns, right? Okay, so this was P, right? This was clear. Okay, so it just all relies on the fact to calculate P. Okay, now let us come back to the question. The question was 1 1 2 0, matrix was 1 1 1 0 2. We had found that its eigenvalues are 1 and 2, right? So we need to find the eigenvectors with respect to 1 and with respect to 2. So let v1 be the eigenvector. So let this be lambda 1, let this be lambda 2. So let vi be the eigenvector corresponding to lambda I. Okay, and let vi have the form, say it's let me not complicate it. Let me not complicate the notation. Let me just simply come out with a result. What is a minus lambda 1 I let A minus lambda 1 I V1 V2 be equal to 0. So V1 V2 will comprise the eigenvector corresponding to lambda 1. So we have A minus I, right? So it's 0 here, it's 1 here, it's 1 here, it's 0 here, right? Then you have here V1 V2, right? So 1 minus 1 is 0, 2 minus 1 is 1, correct? That's 0 0. So obviously this is equivalent, row equivalent to the matrix 0 1 0 0, and you have here V1 V2, right? So carefully observe from here what you have. V2 is 0, right, from the first row. So 0 times V1 plus V2 times 1 is 0. V2 is 0 and V1 is free, right? So therefore we can consider V1 V2 to be 1 0. Okay. Similarly calculate the other part. So suppose A minus 2I, that is lambda 2 times say U1 U2 is 0 0. So this simply gives the fact. So the matrix was 0 1 1 2, right? Yeah. So this is minus 1, this is 1, this is 0, and this was 0 itself, right? Clear? So times U1 U2 is 0 0. Again observe in this case that U2 is free, right? U2 is free, and here you have minus U1 plus U2 equal to 0, and U1 is equal to U2. So simply consider U2 to be 1. So let U2 to be 1, then you have U1 U2 as 1 1, right? So let P to be, so these are one dimensional eigenspaces, right? So only one vector spans the eigenspaces, so we can consider them as bases. If you just know the concept of diagonalizability, then these statements should be clear to you. So you have 1 0, you have 1 1. I have detailed lectures on diagonalization and other concepts related to diagonalization on my playlist. You can obviously go and check them out, right? Okay. And what is P inverse then? So determinant of this is 1, and the adjoint of this should be 1 1 minus 1 0, right? The determinant is 1, so we don't need to keep them up. So let's just observe. So 1 times 1 plus 1 times 0 is 0, correct? 1 times minus 1 plus 1 times 1 0, 0 times 1 and 1 times 0 0, and 0 times you have minus 1 and 1 times 1. Yeah, correct. This is always okay. Therefore, what is e to the power a? So e to the power a by definition is e to the power p times e to the power dp inverse, right? So you have 1 1 0 1 times, what is e to the power d? E to the power d is e to the power 1 and e squared here, right? 0 0. So it's 1 minus 1 0 1, right? How can I write it? So the diagonal matrix D, because we have considered the first eigenvector to be the eigenvector corresponding to the eigenvalue 1. So D considers of the form 1 2, right? Let's just calculate this out. On the left, obviously. So it's 1 times E, so you have E here. You have 1 times 0, you have E squared here. You have 0 times E, so you have 0 here, and you have 0 times, so you have E squared here, right? Times 1 minus 1 0 1. So this comes out to be E times 1, E, so you have E here, E times minus 1 and E to E square minus 1. So you have E square minus E, you have 0, 0 here, and you have 0 times, so yeah. I guess that's what the exact answer we had, right? Let me just go back to the previous page, right? Where was the answer written? Yeah, we had got this, right? So it's obvious, if the matrix is in a form that's the inductive form of its powers is difficult to calculate, then the diagonal form comes as a rescue, right? I guess it's now easy to observe this. Clear? So whenever you are asked to find e to the power a, where a is the powers of a are difficult to calculate with an inductive form, but you observe that a is diagonalizable, then simply go through this method. Okay. Is it clear? Is it clear? Okay. Now is a very important theorem which relates this to differential equations. Theorem, let A belong to the set of all n cross n complex matrices, or you can consider them n cross n real matrices. The columns of the matrix e to the power ta for some scalar a, for some variable scalar t, forms a basis for the solution space of the differential equation dx by dt equals to ax. Clear? Clear? Okay. So proof. So the acha, 1 second. Okay. So recall the statement of the second statement of the first theorem we had. What was the second statement of the first theorem we had? So it says that e to the power ta is differentiable and its derivative is a e to the power ta, right? So we know e to the power ta is differentiable. Now I have used the term here variable scalar. It's quite an abuse of notation. But variable scalar means t can be an arbitrary scalar. I wanted to say that. So let me just change the term by saying it to an arbitrary scalar for some arbitrary scalar. Okay. So e to the power ta is differentiable and differentiable function of t, to be precise, and its derivative is a e to the power t, right? Therefore, if the derivative of e to the power ta is of this form, then it clearly satisfies this. The columns of this will clearly satisfy this differential equation, right? Because each column of e to the power ta comprises of vectors, right? It comprises of vectors, n cross 1 vectors. Therefore, the columns of e to the power ta evidently solves the given differential equation. Okay. So it suffices to show that every solution is a linear combination of the columns. Okay. Therefore, it suffices to show that every solution is a linear combination of the columns. Okay. Okay. So let xt be an arbitrary solution. Let xt be an arbitrary solution. Okay. Okay. We differentiate then d dt of e to the power minus t a x t. What does it come out to be? So it's minus a e to the power minus t a x t times xt. Sorry. We have already written xt plus e to the power minus ta, and you have here the derivative of xt, right? So it comes out to be, yeah. So you have e to the power minus ta xt. So it's minus a times e to the power minus ta xt plus e to the power minus ta e to the power minus ta times axt, right? Axt. Since a and e to the power minus ta commute, therefore the derivative is 0. The derivative is 0. Okay. And why is it so? Because xt satisfies the differential equation. Right? Therefore, dx by dt should be of the form ax. So we have used that. Let me just break it down. If I just break it down, so that it comes out to be dx by dt, dxt by dt, but this is axt. So that's what we are using here. Okay. So you have here axt, right? And these two will obviously commute by the series form of e to the power minus ta. That's quite obvious. Derivative is 0. So if the derivative is 0, this implies e to the power minus ta times xt is a constant column vector. Is a constant column vector by simple matrix multiplication. Right? Say the column is given as C1, C2 till Cn transpose. Right? And xt is simply e to the power ta c. Right? I guess it's obvious now. If this equals c, then xt is e to the power ta c. Right? Therefore, xt is a linear combination. Right? It's quite obvious from this. Is a linear combination of the columns of e to the power ta with coefficients ci. Right? With coefficients ci, and the expression is unique. And the expression is unique as e to the power ta is invertible. Is unique as e to the power ta is invertible. Therefore, the columns of e to the power ta serves as a basis of the solution space. Yes, it's clear. Right. So this is quite a relation of linear algebra with differential equation. Right. And if you recall, the solution space comes out to be of this form, right? Of exponential form of these differential equations, right? Okay. So let this lecture be up till this much. In the next lecture, we will be trying to come up with solutions to some problems regarding Jordan canonical forms and rational canonical forms. Or I should be having 2 to 3 lectures discussing again independently on Jordan forms and on rational canonical forms. Okay. So meet you guys in the next lecture.